Good morning, sir.
Hi, sir.
So good morning. Let us resume back to our discussion on machine learning for image processing lectures. In this lecture, let us continue our discussion on perceptron to neuron, and then let us see the limitations of perceptron and neuron. We will see now in this lecture on the motivation for design of neurons and neural networks, more specifically on the biological aspects which motivated the initial developments. We will also see what are the similarities between the biological neuron and the artificial neuron, and from there we will also see how the neural networks comes out. So I'm sharing this screen now. If you have any questions in the last class, you can ask before we start on to the discussion on new topic of a neuron and motivating it from the biological neuron front. So at the end of the previous class, what I was mentioning is, so if we there are two ways to find a decision boundary in non-separable samples, or when the samples are not linearly separable. So one way is you find out a appropriate nonlinear mapping, wherein in the nonlinear space, okay, the initial feature space is x and nonlinear feature space y equal to f of x. That may be there these samples are linearly separable. That's one way of doing separating the nonlinear samples through nonlinear mapping, nonlinearly separable samples, non-separable samples through nonlinear mapping. So you can separate them. The other way is you project them onto higher dimensions, wherein one dimension comes from the original features. Okay, other dimension may come from another mapping. Let it be non-linear or linear or whatever. Okay, so putting those two together, you get a high dimensional mapping. This is a very crude design of higher dimensional mapping, but there are very elegant ways in which you can map the features to very high dimensions or even infinite dimensions. And through that, you can show that in the higher dimensions, the samples are all very well separable. You can see here, so x and y, if I put two dimensions, if I plot in 2 dimensions the same samples, you can easily separate them. You can see that even the samples of y are also distinguishable, okay, in the higher dimensional representation. And when you put a decision boundary, this is equivalent to, so as you can see, when you put a decision boundary like this, this is equivalent to putting a non-linear decision boundary in the lower dimensions. Okay, so putting a linear decision boundary in higher dimensions is equivalent to putting a non-linear decision boundary in lower dimension. That's what I was mentioning at the end of last class. So if you have any quick questions on this, you can ask. Otherwise, we will move on. Okay, now so let us start the discussion on the neuron. As I said, the development of neural networks or neurons, okay, using neurons for classification was motivated by biological capability of the neurons and neural network. As you know, in our brain, we have millions of neurons and trillions of interconnections between these neurons. That means we have very large number of neurons, and the interconnections between the neurons are also even higher. And what is known or understood is that between assume that this is a neuron, this is a neuron. Neuron has a cell body, and this is called axon, wherein the neurotransmitter substance gets transmitted. Okay, and these are referred to as synapses. Okay, and these are referred to as dendrites. Okay, so what will happen is the neurotransmitter substance gets generated. Say, for example, because of the activity that we subject to, either from eyes or any senses. Okay, some small neuron transmitter substance gets generated in some of the neurons. Okay, when they get generated, some of the neurotransmitter substances, they transmit that through synapses to the connecting neurons. Okay, and through dendrites it reaches, and then it moves through the axons, and then they see this neuron. If we consider, this doesn't only get the neurotransmitter substance from a single neuron. It may get from several other neurons. Okay, the collective information is of neurotransmitter pulses gets accumulated here, and that with it doesn't accumulate directly. It may be accumulated with relative importance given to each of the neurons and their connection strengths. Okay, and then that weighted accumulation, okay, will be non-linearly weighted by this neuron and triggers a pulse. Okay, so if you want to turn on or off, for example, okay, so if a deciding neuron gets neurotransmitter substances or the neurotransmitter impulses or inputs from several other neurons, okay, who collects the information, and all these put together with some collective inference from each of them with weighted inference, okay, this takes a decision based on its non-linear activation or triggering. Okay, so because what we need to do finally is yes or no. Okay, so for that it makes a like a threshold kind of decision you can consider to perform or not to perform an action. Okay, so is this discussion clear? So now let us see. Okay, so what are equivalent to an artificial neuron? See, as we said, the information is given to each, for a given neuron, the information comes from several synapses. Okay, so we can consider that each of the synapses provides an input to the dendrites. Okay, so this strength of like the input information from each of the synapses, okay, is what? It can be mapped to which of the mathematical quantity in our discussion. Okay, what we have, I will list here. Let us see what we want to map. This is biological and this is artificial. So what we are trying to bring is, we have the model of biological neuron here. We want to bring out the model of artificial neuron as well. Okay, so and then we want to see what biological aspects map onto what artificial in the artificial neuron. Okay, so in that discussion, what I have mentioned is the input for this neuron. For example, if you consider this neuron, okay, input can come from many other neurons. See, if you get from 3 different neurons, do you take the input of all 3 neurons equally, or will there be any different, or how do we take it? That's the question.
So some weight would be assigned, I guess.
Yeah. So if we are given, say, if I ask you to answer a question, okay, if you don't know the answer, if you ask 3 of your friends, okay, then each of them might have told slightly differently. So will you take with equal weight with all these answers? Oh, yes or no?
No, sir.
You will have a preference, right? So you know based on whatever, okay, your intuition as well as the students' understanding, you may give relative weights and then take them. So these inputs, now what I'm saying is these synaptic strengths. So each of these connections will have different strengths with which they get connected. Okay, so here the synaptic strength information from a synapses is what we will see later. This first thing. Okay, second thing is synaptic strength. So it is, what I'm conveying is the synaptic strength is different from each of the synapses. So in real cases, that what we are considering as weights. Okay, different weights we give. Now, given that it's collective information here, we take the collective information. So and then this collective information is used to help this neuron to take a decision. Now the question is, how does this neuron trigger? Okay, based on this collective information. Okay, that we will see subsequently. So let us start the model of artificial neuron. What are all the input information? What should we consider it as information from synapses as? in the artificial neuron? What do we have as input to take a decision?
Features.
Any?
Features.
Yeah, feature values. So x2 up to xd. These feature values can be of class 1 sample or class 2 sample. If it is class 1 sample, okay, if this belongs to class 1 sample, the neuron has to finally convey as a label, that is y is equal to, okay, y belongs to class 1. Fine, it should say that it belongs to class 1. If x belongs to class 1, correct? Else, it should say that otherwise. Is it fine or not? Now, how do we take them? Do we take with equal weight all these input features? What do you suggest? Huh? We give relative importance. Okay. So let us put some weights here. W1, W2 up to WD. Okay. Let us put different weights because each features measured also need not be treated with equal weight. Fine. And these put together, we need to take a decision, right? So decision should be taken putting all these things together. Correct or not? Fine. Okay. Yes. And this is what, and here we should have, finally we should get y here. Okay. So the output of the neuron. This is the model of artificial neuron. See what should happen in between here. The summation of all these things should happen. Correct? Weighted sum of all these things. In addition to that, as I mentioned, okay, we want to map the final answer to a yes or no kind of answer. So there can be a nonlinear mapping like thresholding. Okay, so this put together is an artificial neuron. Now, y equal to what? In now mathematical terms, will you be able to tell what y should be? In terms of x1 to xd.
Sigma wi
x1 w1 plus yeah, fine, good. So somebody is telling the xd wd. See, in addition to all these things, we also may have a bias. Bias is what, in some sense, its own intuition, because see, even if all of them say some answer, I may not agree to it. Okay, I may have a strong intuition that it is not correct and I may have put other answer. Okay, in the similar manner here, the individual bias, the neuron itself, which is taking a decision, can have it. Okay, so that is bias. Fine. These put together is what is the expected output y plus bias. See, but what is this? This is only the net value. So let me write y in 2 steps. Okay. So we'll essentially get y here, but this is the net value before y. Okay, and y is equal to what? F of net value. Is it fine or not? This net value now can also be written as in summation form is equal to, how can I write? Huh? Somebody was telling xi wi, I equal to 1 to d plus b. Is there any other way of nicely writing this net value at the given neuron? Huh? What is that? Yeah, vector form. How should I write? W transpose x plus b. Is this fine or not? Yes?
Yes, sir.
Okay. So now what you see here, see if I give sample xk, what I'm essentially getting is yk, which is equal to f of, okay, W transpose xk plus b. Yes or no? And if this f, if I consider it as, say, f as a threshold activation function, then what does it mean? If W transpose x plus b is greater than 0, I put to one class. W transpose x plus b less than 0, I put to second class. Yes or no?
Yes, sir.
In that case, do you see any similarity with respect to this artificial model of neuron and the perceptron? In what way this is similar and what way this is different, or anything that differentiates this and that? Can you mention? Need your quick answers on this.
In perceptron, F is linear.
Okay, F is linear, you are saying. Why do you think F is linear here in perceptron?
Basically, we are not assigned anything.
Huh?
Basically, we are not assigning.
See, even in perceptron, what I'm saying, if W transpose X plus B greater than 0, I'm putting to one class. W transpose X plus B less than 0, I'm putting to other class. So in that way, F is nonlinear only, right? F is what? Y. So if I want to strictly put it, okay, let me put here. YK. Okay, YK, Y is equal to 1 for XK belongs to omega 1, and it is minus 1 for XK belongs to omega 2. See, this is same as in perceptron and even here, is it not? So for this, what I'm saying, F is a threshold activation function or threshold nonlinear function. If W transpose X plus B is greater than 0, I am putting it as plus 1. W transpose X plus B is less than 0, I am putting as minus 1. Is it correct or not?
So in previous perceptron, Y was equal to W transpose X plus B only, no?
Okay, so fine. So for notation wise, Y equal to W transpose X plus B, I have put. Okay, but that's only a notation. Okay, but the decision what I take is label if I want to give to that. So I am just looking at, do I look only at the magnet sign of that, or do I also consider magnitude of it?
They're only sign.
See, in our previous discussion, somewhere if I might have written Y equal to W transpose X plus B, okay, that's only to relate. So the actually what I look is sign of Y, is it not, to put into class 1 or class 2?
Yes, sir.
So in that way, that's actually, this is the more appropriate way of writing. So Y equal to F of, where F is giving the sign of. Okay, if you want to think in terms of that, so Y equal to say F equal to, okay, sign function here. Okay, it's the same as threshold function. Greater than 0, one class, less than 0, other class. Is it fine or not?
Yes, sir.
Right. So now let us bring in the artificial neuron. What does these map to? The first one is information from synapses. This maps to what in artificial neuron?
So features.
Yeah. Feature values. Okay, that is input features denoted by XK. Okay, XI. Okay, and then what is synaptic strength?
Weights.
Weights. Okay, synaptic strengths are equal to weights. WI. Okay, and then output from axon is essentially what? Output from neuron. That's our artificial neuron. That is Y. Okay, is this fine? YK you can consider if I am considering XK.